Hi everyone, welcome to our video on finding the intervals of concavity and inflection points for a polynomial function right here. Alright, so in this example it says find the domain and then determine the intervals on which the functions are concave up or concave down and find the inflection points. Alright, and we're just going to break down these steps as we go. But first, let me actually underline, if it ever says concave up or concave down or inflection points, I would think get these two eventually involved to help you out. So those are the signs of the derivative, second derivative, f double prime sign, so positive or negative, and then this is the concavity, at least sort of the shape of it, concavity of f. All right, so let's break down our steps. So the domain can be pretty nice most of the time. So this is a polynomial. So a polynomial has positive whole number powers. The 5 and the 4 are positive whole number powers. So that means the domain is all real numbers. So negative infinity to infinity. Okay, so that's good. And then moving on. 2. Let's now find the second derivative of this function. So to find the second derivative, you need the first derivative. So f prime of x, well, 1/20th would get multiplied by 5. So I did the power rule with the x to the 5th there. Minus 1/12 would get multiplied by the 4x cubed. So I used the power rule on that too. And then this would simplify. F prime of x is, well, 1/20th times 5 would become a 1/4. And then x to the 4 minus 1/12 times 4 would become 1/3 and then x cubed. So there's the first derivative. This is useful for increasing, decreasing. As a reminder, good for increasing, decreasing, and relative extrema. Okay, so if that's what they wanted, that's what we would continue to use. All right, but we have concavity instead, so let's keep going. So f double prime of x, well, this 4 would multiply the 1/4, and that would give us just 1. Minus 4 from that power would be cubed. Minus the 1/3 times 3 would give us 1, and then minus 1 from the x cubed would give us x squared. There we are. And then just like with a first order derivative, it's usually best to factor these problems. So f double prime of x, notice x squared's in common, so we have x squared, oops, not x squared minus 1. We have x squared in common, and we're left with x minus 1. And remember, you can always check with a quick multiplication. There we go. And then I'm going to cloud this because it's useful for us for multiple parts. And it is very similar to what we did with the first derivative, where now I'm going to find the critical numbers. So I'm going to set this equal to 0. So now we're doing step 3, where I set the derivative equal to 0. And then we'll set all of our factors equal to 0 to solve. And so this first one, well, it is just going to be x equals 0. That's the only option there to make 0 squared equal to 0. And then add 1, x is 1. Okay, so these are the critical numbers for the second derivative. So they're the critical numbers. So there's critical numbers for the first derivative. There's critical numbers for the second derivative. These are the critical numbers for the second derivative. All right, and then now that we have those, we're going to do our number line again. So number 4. So let's just keep going vertical. So here's my number line. Hopefully that's big enough. And I've got, let's put 0 here and 1 here. And then these are x values. Now the only thing that changes is I still want to mark f's up here, or types of f's. And here I will want my second derivative that I'm going to do in blue. And then just my original f. Okay, so I want to know the sign of the second derivative. And then that would tell me how f has its concavity. All right, so let's start plugging in. So I have my clouded function here, and I want to plug in something bigger than 1. So I'm going to choose f double prime. Anything bigger than 1, I'm going to do 10. And then if I plug it into my clouded expression, so I already changed that first x. I want to plug it into here. 10 squared is 100. 10 minus 1 is 9. And so this is 90, but what's important about it is that it's positive. So a little plus. And then I want to choose something in between 0 and 1. Okay, so I'm going to choose x equals 0.1. So that's bigger than 0 and less than 1. And then we want to plug it into our second derivative. So again, the clouded one. If I plug it in, 0.1 would get squared times 0.1 minus 1 would be negative 0.9. Well, 0.1 squared is positive. Negative 0.9 is negative. So a positive and a negative makes negative. Okay, so and again, all I care about is the sign. If you really want to, you could really verify with a calculator. You can start to plug those in. But I'm doing it kind of the quicker way with just thinking of only the sign that's important. All right, and then one other time, I want to choose something less than 0. So let's do x equals negative 1. And so I have f double prime of negative 1 would equal negative 1 would get squared. And then negative 1 minus 1 would be just negative 2. Well, negative 1 squared is 1 times negative 2. This is negative, which again is all I care about. And notice I could actually quickly, easily do that. It is negative 2. But the main thing is I know that it's negative there. Okay, and so now that I have my symbols listed on my number line, I want to reference these two again to help me with the concavity. Okay, so this is step 5, finding those intervals as well. So now we're at step 5, where I'm just thinking, all right, well, let me just draw these guys again. Hello and hello. Okay, so these are the signs of our second derivative, and this is how the concavity of f is. All right, well, my sign, if I'm reading this left to right, so this is negative, so that makes this type of concavity. So it's like this somehow, which in words would be concave down. This negative also tells us it's something like that, which is concave down. And then this positive would be concave up. Like that. Okay, so it looks like we have our intervals. Okay, so we have our intervals to where it increases, decreases, so determine the intervals. Okay, so that is still our number 5. We want to actually state it in interval notation, so still number 5. I have concave down from negative infinity to 0. And then we do break up the interval, so it is concave down and then another concave down, but something weird is happening at 0, so that's why we want to split this up, and we'll plug it into the calculator to show it. Okay, but then it is concave down again from 0 to 1. And then it's concave up from 1 to infinity. Okay, so there's our concavities. And then now we need the inflection point. So the inflection points. So on this one, there is just going to be a single point. So it's where the change in concavity occurs. And well, it's concave down to concave down. So there's no change in concavity. Here's where there's the change. So concave down to concave up. Here's our inflection. Let's just abbreviate it. INFL, inflection points occurs. I'm going to highlight it in pink at x equals 1. So the inflection point, so on this problem, it's not an S, it's just point. So the inflection point is at x equals 1, because that's the only time it changes concavity. But they want the actual point, so that means plug it into your function. So f of 1 is what we want to use. And then we need to go back. Well, here's our f of x, so I'm changing my x's into 1s into this problem. So I have 1/20th times 1 to the 5th, and then minus 1/12 times 1 to the 4th. Well, 1/5 and 1 to the 5th and 1 to the 4th are each 1. So f of 1 is 1/20th minus 1/12. I think 60 is the smallest common denominator, so that means this one I would need to times by 3. This one I would need to times by 5. And so we would get f of 1 is 3 minus 5 over 60, which is negative 2/60ths, which becomes negative 1/30th as a fraction. So our actual inflection point, so the inflection point is the x-coordinate that we used, 1, and then our y-coordinate that we found after, the negative 1/30th. So that is our inflection point, like that. Okay, so, but with concavity and just like increasing, decreasing, our calculator sure can help. All right, so I'm going to go to our graphing calculator, and I usually just use Desmos, desmos.com/calculator. And then we get, let's plug in the actual function. So it was 1 divided by 20, x to the 5th. And I'm using my arrow key just to make sure everything's, so it should look exactly as typed there. So don't put that x down there. That would be a mistake. Okay, so move the arrow first, and then you could do your 4th power. Okay, so there we go. Okay, so and then I want to check with my concavity statement. Let me make it a little bolder. Okay, so here is, let me scroll up just a little bit. So here was our number line. Let me try to get that in view with the calculator. Okay, so there's both of them. Okay, and notice it's concave down and concave down. And we can see here's concave down. So something weird's happening at 0, but there's no inflection point. It's most likely just perfectly horizontal for that split moment there, split second moment. Okay, so that's why nothing's really happening. And then from 0 to 1, it's still a frown. Okay, so still frown. So this is matching. And then notice at 1, oops, well, that's 1.3. Okay, so it's not showing the inflection. Okay, so but we can eyeball it. There's 1, where it does look like after that, it does look like it starts to smile there a bit. So there's our 1 right there. Okay, so it didn't mark it. So inflection points, it doesn't mark, it seems. Here I've got 2 other important things. That solid dot looks like it's where the minimum would be, the relative minimum. This is the x-intercept, so that's why these are there. Okay, so this solid dot currently is important if they said what's the relative minimum, but it's not important for this problem. We wanted just the inflection. And again, our 1 value, let me zoom in. So at 1, we've got this scenario, and it does look like that is where the change occurs. Let me go ahead and put that 1. So 1 comma negative 1 divided by 30. So that is the point that we found. I'm using the fraction of it. Okay, so that's that point right on that graph. And notice left of it, it does look concave down. Right of it, it does look concave up. So it looks like we did it correctly. Okay, so that's that. So we've got it. If you have questions, please let me know. Otherwise, you've got, I'm going to do these 2 in separate videos, but you're welcome to try them out on your own, and maybe skip my videos if you wanted to, or at least fast forward to verify your answers. Okay, but it's very much the same where we're going to break down this process. All right, so thanks for watching, and I'll see you again next time.